Welcome to Maths with Bob. Today we're looking at matrices and we're going to be diagonalizing a matrix A over here. Obviously to diagonalize a matrix we need the eigenvalues and eigenvectors, and basically we have the diagonalization of this matrix A is in fact basically a matrix with the eigenvalues down the diagonal, and we'll have a look at this in a minute. So what do we do? Well, the first thing we have to do, I'll just grab a highlighter, is first of all, it goes back to solving this equation, and it's a matrix equation. Well, not as it stands. We need to multiply by lambda, the eigen. Okay, lambda is a real number. Okay, it's a scalar. We need to multiply by I. Okay, the identity or unit matrix of the same size as A, just to make it a matrix equation. So we have to solve this equation. Okay, this is the equation we have to solve. Now, a few things. Well, okay, A, this is obviously our original matrix over here. Okay, lambda is going to give us okay, the characteristic equation we will see in a minute down here. And x is this one here. Obviously, this is going to be the eigenvector. So we need to solve this, if you like, this matrix equation for the eigenvectors. And each eigenvalue has an eigenvector associated with it. Okay, now the procedure is, okay, so we need to find the determinant of a minus lambda I. So we need to put it all into here. And we get what's called the characteristic equation, characteristic polynomial. This is the characteristic determinant. So we end up getting this thing here, okay, the characteristic polynomial, and we need to solve this for the lambdas, okay. Now we actually, this is degree 3 polynomial, so we actually need 3 distinct. This is something we're going to be looking at later on too, that for a matrix to be diagonalizable, it needs, if it's a 3 by 3, it needs 3 distinct, real, okay, and different, for that matter, eigenvalues, and obviously eigenvectors as well. So how do we do it? Well, obviously we have to go about in turn, putting the minus, let's put the minus 2 in here first, but we have to put in minus 2, 2, and 3 in turn into the characteristic determinant, augment it, use Gaussian reduction, and try and find the associated eigenvector, okay, for that particular eigenvalue here. All right, so first up, if you put in, well, I should go back and actually didn't mention here that if I have a quick look down the bottom, what do we have? We got, we can see here we've got what, 4, say that's xy, 4y is 0, and minus 8y is 0. So obviously y is 0, and if you put y as 0 into the top one, obviously x 0, and we're obviously going to make z a usually as standard. So we let z equal a, so we can get here that x minus a is equal to 0, x is equal to a. So that's going to give us the vector, which I jumped ahead a second ago. So z's a, x is a, and y is 0, right? So we should eventually get here the general vector, okay, over here. And you can see here the general vector a 0, a. And put in a as 1 to get a particular, okay, particular vector for that particular eigenvalue of minus 2. Okay, so here we have our particular eigenvector. And we go ahead and do the same process now. Let's change the color. So go back to yellow. Okay, so we now put in 2. And we put the 2 back into the characteristic determinant. We augment it, use Gaussian reduction to try and reduce it. Now, you can see here from row 3 that we have that 1 x is equal to 0. So obviously x is 0. Okay, x is 0 here. You can see here. You let z equal a, and then you work out what y in terms of a minus a on 2, and you end up getting this eigenvector here. Okay, and a particular one, obviously you've got a half here, so you let a is 2, and you can see here we end up getting, okay, this eigenvector x2, okay, for the particular eigenvalue of lambda equals -2. So we're well on the way. Okay. All right. Now, finally, we had to put in lambda is equal to 3 into the characteristic determinant into here. Well, 3 minus 3 is actually, you can see -6. And obviously, you put it all the way down the diagonal, you augment it, and then you try and use Gaussian reduction on the augmented matrix here, basically to try and solve the system. And we can see here we've got, well, what, minus, we can actually make this row 0 quite easily, okay, just by, if you like, quite simply, oh, I've done it down here actually. Okay, I'll just row 3 minus row 2. So row 3, okay, yeah, -4, -4, 0, okay. You get -5, -5, 0, 0 here as well. So end up obviously make a row of zeros. You can quite easily do it from here. You can just see here, it's going to be 0 on the bottom there. So we let z equal a. And then from row 2, we have -4y, -4y minus 5a is equal to 0. And then we end up getting y is -5a on 4. And from row 1, we substitute in, obviously, these values, z's a, y, we're going to back substitute to be, so it's -y, so it's -5a on 4. And then we work out what a is. Okay, so we've got z's a, eventually, we have y over here as well, y -5 on 4a and a. So we end up getting, this is our, okay, our eigenvector for our lambda equals 3 value. And a particular one, obviously we've got 4 as a denominator, so we let a is equal to 4 to give us a particular, okay, eigenvector, okay, x3. Okay. All right, now we're now in a situation to start forming our matrices. Okay, now obviously our diagonal matrix here, we've got all the eigenvalues you can see here, down here, and we've got all our eigenvectors in C here. Okay, now there is a bit of a theory. We are going to use the idea of diagonalizing to form a to the power 4. We're actually going to find the power of the matrix A. Okay, so we basically, if you haven't watched the other video, but there is I mentioned briefly at the end there a bit about diagonalization, and you can see here we use the eigenvalues and eigenvectors to diagonalize the matrix. Okay, we say the matrix D is the diagonalized A. So this is D. This is a diagonalized A. And it is similar to matrix A. It's a similarity transformation. Just beware. You can see here, not all matrices can be diagonalized. They actually need n different real eigenvalues and vectors. But basically what we do is to get the diagonal matrix D, we need to go C minus 1, which is the inversion of C, or well, I guess you could say the reciprocal of C. Okay, we just normally say it's the inverted matrix C times A, the original matrix, and C, which is now this one here, the associated eigenvector matrix to the eigenvalue. It's here, and that's actually equal to D. Now, so A is the, if you like, the original matrix, D diagonal eigenvalues, C, you can see here, the eigenvectors. Now, you're going to need to compute this inversion of C, inverted matrix C, okay, here. But basically what happens is, if, say, for instance, I want to work out what D squared is, actually, okay, so D squared is equal to C to the minus 1 AC by C to the minus 1 AC. You can see here that the C and the inversion of C will cancel each other out, okay, so we end up getting what? A times A, okay, A times A is going to be A squared. We're going to have C to the minus 1 and C. Where's C? C on the end here. Yeah, so we're going to get C to the minus 1, A squared, C. So D squared, which is pretty easy to square a diagonal matrix. Okay, and we keep on going. So we basically generalize this, that the diagonal matrix to the power n is actually the inversion of C times A to the n by C. Now we need to rearrange this, okay, so we need to make A to the if you like, a to the n, the subject to this formula. So, okay, so we need to basically multiply on the left and the right of this to make a to the n, okay, the subject. And this is the thing we're after. This is the power of the original matrix A to the power n is equal to C. Okay, this is the matrix over here, C times d to the power n, which is this matrix here, raised to the power n, times the reciprocal of C. Okay, so we're going to need to find C to the minus 1, okay, to actually evaluate A to the power 4. All right. Now, a couple of things. Obviously, to find the reciprocal, it needs to be non-singular. Okay, so I just worked out the determinant here. It's 5. It's okay. So the determinant's 5, so it's non-singular. Okay. All right. Now let's go through the process of finding the inversion or the inverted matrix C, the reciprocal of C, I guess you could say as well. The actual command in GeoGebra is invert matrix actually. And so how do you find it? Well, you need to find what's called the cofactor matrix. Okay, cofactor matrix is this one here. Wow, this is a monster. This is the cofactor matrix. Okay, the cofactor matrix is really massive. It's obviously comes from C. C is whoa. Okay, here's C. This is our original C, okay, which was, you might remember, just the matrix of the vectors, the eigenvectors associated with the eigenvalues in D, the diagonal matrix. Anyway, so what do? Well, basically, we need to replace each element by its cofactor. Now, this can be a little bit confusing to say the least, because you're not actually using these numbers, you're replacing them by their cofactor matrix. Well, the cofactor is actually a determinant. I shouldn't say cofactor matrix. We form the matrix. It's a cofactor matrix. Each of the cofactors are in fact determinants, and it's a bit confusing. So basically what happens is you have to be careful with determinants. They go one positive, negative, positive, negative, positive, negative. Okay, so basically it's -1 to a particular power I plus j, the row and column. So basically they alternate in sign, but what happens is, let's have a quick look. Suppose let's actually go here and have a quick look. So for this particular element, 1, I need to replace it, okay, with its cofactor matrix. So what do? Well, I cross out the row and the column, and I look at the determinant of what's left, this bit here. Okay, so that bit there, okay, is the cofactor matrix of that element 1. Now it's positive, it's in the first spot. So let's go through the next element. Okay, so this one here, so I want to find the cofactor matrix. I should say, well, I shouldn't actually say cofactor matrix. It's actually, the cofactor is actually a determinant, but I want to put it into a matrix, and so it's the wording. So I need to actually cross out this row and this, I should say that column and that row, and basically have 0, 1, minus 5, 4, 0, 1, minus 5, 4. So basically zeros, that element in that particular matrix C of the eigenvectors, is replaced in the cofactor matrix by the cofactor itself, which is actually a determinant. Okay, but it has a negative sign because in determinants they alternate in sign. So as I said, it gets a bit confusing. So basically, eventually, you form what's called the cofactor matrix by forming the cofactors of each of the elements in the original matrix C, which was coming from the eigenvectors. Actually, those vectors came from the eigenvalues for the particular matrix A. Anyway, so here we have. So we form the cofactor matrix here. So this is the cofactor matrix C to the power C. Now, okay, we now have to transpose the rows and the columns to form what's called the adjoint matrix. Okay, so we basically then transpose it to get the adjoint matrix C to the power A. So this is our cofactor matrix. We obviously write this column as this row, okay, or if you like, this row as that column. Okay, so we transpose the rows and columns basically. And then to get the adjoint matrix, okay, C to the power A. And then we divide the adjoint by the determinant of C, which we worked out earlier was 5. So eventually we end up getting that, here we have, with a lot of work, this is now, you can see here, this is our inverted matrix C. It's actually a bit tricky because it has dividing by 5, so we've got decimals basically coming throughout here. Okay, all right, so that was a fair bit of work involved in there. Okay, all right, now how do we actually work out what a to the power 4 is? Okay, so we're going to raise the original matrix over here. This is the original matrix over here. We want to raise it to the power 4, right? Now, you could, I'm going to actually go into, in a minute, go into GeoGebra and actually show you how to do it in GeoGebra. It's pretty easy in GeoGebra, but obviously you can go a to the power 4. But what we want to do is we want to actually use our eigenvectors and eigenvalues to work this out. So what we have to do is we need to, as I said, rearrange the original expression with the diagonal. So we need a to the 4 is equal to C, original, okay, matrix of the, you can see here, the eigenvectors, okay. Our D, which is the eigenvalues down the diagonal, so this is D, but it's raised to the power 4. So to raise a diagonal matrix to the power 4, you just raise each of the elements on the diagonal to that particular power. And now you have to multiply it by this inverted C, which is C to the minus 1 here. Okay, so this is the reciprocal of C, or the inverted matrix. I perhaps should say inverted matrix, a reciprocal of a matrix. 1 over the matrix, I suppose, is, well, it may not be interpreted exactly as the inversion of C, but it's meant to be in my particular situation, okay, in this particular case. So the idea is that we now need to multiply this matrix by this matrix, and then finally by that matrix here. Now, okay, matrix multiplication is not commutative. It is associative, but it's not commutative, so we have to be careful. We have to multiply this one by this one and then by that one. So we end up getting basically, here we have a to the power 4. So finally, this is our answer down here at the bottom here, that when we raise our matrix A, our original matrix A, which was over here, this is our original matrix A, to the power 4, this is what we get: 3, 26, 13, minus 65, 146, 65, 52, minus 104, and minus 36. Okay, so let's actually just pause for a minute and we'll, well, here we have GeoGebra 5. Let's actually create some matrices. Now you might remember you highlight, in spreadsheet view, highlight your matrix, right click, create a matrix, create matrix. Let's call it, rename it, Shift A, okay. Okay, so this is matrix A. Now, we can just check our answer, so we can just go down into input and go A to the power of 4, that's a little hat, 4, enter, and here we go. This is the matrix raised to the power 4. This is A power 4. Okay, right, so this is A to the power 4. That's not too bad. Okay, you can also do some pretty other things just to check your inversions, I think, which is always a good idea. So this is matrix C, and I'll just create a matrix. Let's call that, rename to C. Okay, and then in the input bar, you just type in invert. Now, our contextual menu will come up. You hit invert with the matrix, and then you just type in the matrix, which is C, which we want to invert. Okay, and then press enter. And you should see here, this is the inverted C. So invert C. Okay, all right. So that's our inverted C. All right. So this is, I mean, it's a great tool, GeoGebra, just to check your answers, rather than going through all the diagonalization, which is quite involved. Okay, I've also got some examples which we can actually have a go at. So hold on. Okay, so let's actually just go across to some examples. Okay, here we are. So I've actually basically given you a few extra examples to have a go at here. The two matrices you can see here, I'll just rename them, keep them constant, simply called A. I've done most of the answers down here. You can see here for exercise 2 and exercise 3, but you can go ahead and check these, and it's always a good thing to work through and try and work out, the characteristic equation, work out the eigenvalues and then the eigenvectors, put them into C, put the eigenvalues down in the diagonal D, work out the inverted matrix C, and then work out what a to the power 4 is. I've actually just kept it a to the power 4. Now, you can actually just go a times a times a times a as well, but as you can imagine, as the power gets higher and higher, this is going to get more and more complicated, and this is a very useful technique for basically solving, if you like, powers of matrices. All right, well, thank you for watching, and bye for now.